Hello students, welcome to MSN Digit Max. I am Ramalakshmi, Head Department of Mathematics, Madurai Sivagasi Nada's Pioneer Meenakshi Women's College, Puvandi. This video is the learning resource for Module 1 of Unit 2 in Sequences and Series 22BMA2C2. In this video, we are going to cover the topic Behavior of Monotonic Sequences. Before starting with the behavior of monotonic sequences, let us recollect what is monotonic sequence. In Module 2 of Unit 1, we have studied what is monotonic sequence. A sequence AN is called a monotonic increasing sequence if AN is less than or equal to AN plus 1 for all n values. A sequence AN is monotonic decreasing sequence if AN is greater than or equal to AN plus 1 for all n values. We have also studied what is meant by bounded above and bounded below in Unit 1. A sequence AN is called bounded above if there exists a real number k such that AN is less than or equal to k for all n values. If we can say k is the least upper bound if k1, k1, k2, k3, etc. are also upper bounds. K is the smallest among all these upper bound. Then we will say k is the least upper bound. Suppose there exists some km which is less than k, then km will not be the upper bound of a sequence an. Similarly, a sequence an is bounded below if there exists a real number k such that k is less than an for all n. That is, an is greater than k for all n. Now we come to the important theorem in the behavior of monotonic sequences. The theorem states that a monotonic increasing sequence which is bounded above converges to its least upper bound. A monotonic increasing sequence which is not bounded above diverges to infinity. A monotonic decreasing sequence which is bounded below converges to its greatest lower bound. A monotonic decreasing sequence which is not bounded below diverges to minus infinity. Let us start with the proof of the first part. Let us take a monotonic increasing sequence AN which is bounded above, and let us assume that k is the least upper bound of the sequence. As we have taken k is the least upper bound, by the definition of boundedness, an is less than or equal to k for all n. Now let us take epsilon greater than 0 be given. Clearly, k minus epsilon will be less than k and k will be less than k plus epsilon. And also, by the definition of least upper bound, since k is the least upper bound, k minus epsilon cannot be the upper bound of sequence am. Therefore, there exists some value am such that am will be more than this k minus epsilon. Because k minus epsilon is not the upper bound, there exists some element in the sequence which is greater than k minus epsilon. We know by definition, by the hypothesis, an is monotonic increasing. Therefore, whenever n is greater than or equal to m, an will be greater than or equal to am. Therefore, an is greater than or equal to am. Am is greater than k minus epsilon. Therefore, we have an is greater than k minus epsilon for all n greater than or equal to m. So, taking the first one, that is an less than or equal to k, and the second one, an greater than k minus epsilon, we have the inequality k minus epsilon is less than an is less than or equal to k. And clearly k is less than k plus epsilon. Therefore, we have absolute value of an minus k is less than epsilon for all n greater than or equal to m. Therefore, sequence an converges to k. K is the least upper bound. Therefore, the sequence converges to its least upper bound. The first part is over. Now let us prove the second part. The second part hypothesis says that if sequence an is a monotonic increasing sequence which is not bounded above, then the sequence will diverge to infinity. Now let us take sequence an is a monotonic increasing sequence and it is not bounded above. When it is not bounded above, we cannot find a real number k such that all the elements in the sequence an are less than k, right? So, since sequence an is not bounded, there exists m belonging to n such that am is greater than k. Also, since sequence an is a monotonic increasing sequence, whenever n is greater than or equal to m, an is greater than or equal to am. Therefore, an is greater than or equal to am is greater than k. Therefore, we have an is greater than k for all n greater than or equal to m. Then by the definition of divergence, sequence an diverges to infinity. Hence, we proved the second part. Now let us prove the third part. The third part hypothesis says that if sequence an is a monotonic decreasing sequence and if it is bounded below, then if we take it has a GLB L, then the sequence will converge to that L value. So let us take sequence an is a monotonic decreasing sequence. Let L be the greatest lower bound of the sequence. Therefore, by the definition of bounded below, we have an is greater than or equal to L for all n. Now let us take epsilon greater than 0 be given. Clearly, L minus epsilon is less than, L is less than L plus epsilon. Therefore, L plus epsilon cannot be the lower bound of the sequence because L is the greatest lower bound. Since L plus epsilon cannot be the lower bound, there exists am such that am is smaller than L plus epsilon. Because an is a monotonic decreasing sequence, an is less than or equal to am whenever n is greater than m. Therefore, we have L is less than or equal to an less than L plus epsilon for all n greater than or equal to m. Clearly, L minus epsilon is less than L. Therefore, we have L minus epsilon less than an less than L plus epsilon for all n greater than or equal to m. Therefore, we have absolute value of an minus L less than epsilon for all n greater than or equal to m. Therefore, sequence an converges to its greatest lower bound L. Hence, we proved the third part. Now, let us come to the fourth part. The fourth part says that if the sequence an is monotonic decreasing sequence, if it is not bounded below, then this sequence will diverge to infinity. Now, sequence A and B, monotonic decreasing sequence, which is not bounded below. Let us take k less than 0 as a real number. Since an is not bounded below, there exists an element am belonging to the sequence such that am is less than k. Since sequence an is a monotonic decreasing sequence, an will be less than or equal to am whenever n is greater than or equal to m. Therefore, sequence an is less than k for all n greater than or equal to m. Then by the definition of divergence, sequence an will diverge to minus infinity. Hence, we proved the theorem. The above theorem gives an important result that whenever a sequence is a monotonic sequence, then it will either converge or diverge. It cannot be an oscillating sequence. So, whenever we are given any sequence, it is enough if we find out whether it is monotonic increasing or decreasing. Suppose it is monotonic increasing, if we can find its least upper bound, then it will converge to the least upper bound. If it is monotonic increasing and it is not bounded above, then it will diverge. Similarly, if a sequence is monotonic decreasing, if we can find its upper bound, its lower bound, then it will converge to the greatest lower bound. If it is not bounded below, then it will diverge. Now let us see the problem. The problem statement is, if the nth term of a sequence an is 1 plus 1 by 1 factorial plus 1 by 2 factorial plus etc. plus 1 by n factorial, we have to show that limit n tends to infinity of an exists. That is, sequence an is convergent and the converging value lies between 2 and 3. Now let us see what is a1. a1 is 1 plus 1 by 1 factorial. a2 is 1 plus 1 by 1 factorial plus 1 by 2 factorial. So, clearly sequence an is a monotonic increasing sequence. Now, let us take the nth term an as 1 plus 1 by 1 factorial plus etc. plus 1 by n factorial. Now, 1 factorial is equal to 1 factorial. Therefore, its reciprocal 1 by 1 factorial is equal to 1 by 1. Similarly, 2 factorial equal to 2. Therefore, 1 by 2 factorial is equal to 1 by 2. 3 factorial is greater than 2 square. That is, 3 factorial is 1 into 2 into 3, 6 is greater than 2 square, 4. Therefore, its reciprocal is 1 by 3 factorial is less than 1 by 2 square, that is 1 by 4. If we proceed like this, we have n factorial will be greater than 2 power n. Therefore, its reciprocal 1 by n factorial will be less than 1 by 2 power n. Therefore, an is less than or equal to 1 plus 1 plus 1 by 2 plus 1 by 2 square plus etc. plus 1 by 2 power n. And also we know that 1 plus r square plus etc. plus r power n minus 1 is equal to 1 minus r power n divided by 1 minus r when r is less than 1. Now 1 by 2 is less than 1. Therefore, this part will become as 1 minus 1 by 2 power n divided by 1 minus 1 by 2. Therefore, we have an is less than or equal to 1 plus 1 minus 1 by 2 power n divided by 1 minus 1 by 2. Therefore, we have 1 plus 1 minus 1 by 2 power n divided by 1 minus 1 by 2 will become 1 by 2. So on simplification, we have 1 plus 2 into 1 minus 1 by 2 power n. This is equal to 3 minus 1 by 2 power n minus 1. So from 3 we are subtracting a smaller value. Therefore this value will be smaller than 3. Therefore an is less than 3. Therefore sequence an is bounded above. Already we have sequence an is a monotonic increasing sequence. We have proved that it is bounded above. Therefore, it has a limit. That is, sequence an is a convergent sequence. Therefore, limit n tends to infinity of an exists. The value starts with 1 plus 1 by 1 factorial plus etc. Therefore, we have a minimum guaranteed value of 2. Therefore, we have 2 is less than, an is less than 3 for all n. Therefore, we have the given sequence an is convergence and the convergent value, limit value lies between 2 and 3. Hence, we proved the problem. The second problem says, show that the sequence 1 plus 1 by n the whole power n converges. Let us take the nth term of the sequence an. An is 1 plus 1 by n the whole power n. The binomial theorem says 1 plus x the whole power n is 1 plus nx plus n into n minus 1 divided by 2 factorial into x square plus etc. plus the last term will be n into n minus 1 into etc. into 1 divided by n factorial into x power n. Therefore, by binomial theorem, we have an equal to 1 plus n into 1 by n plus n into n minus 1 divided by 2 factorial into 1 by n square plus etc. plus 1 by n power n. So, the first term is 1. N and n gets cancelled, therefore 1. Now, in the numerator, take n square outside. N square and n square gets cancelled. We have 1 by 2 factorial into 1 minus 1 by n. The next term, n cube is taken outside. N cube and n cube that gets cancelled. We have 1 by 3 factorial into 1 minus 1 by n plus etc. 1 minus 1 by n into 1 minus 2 by n plus etc. The last term will become, taking n power n outside, n power and n power n get cancelled. We have 1 by n factorial into 1 minus 1 by n, 1 minus 2 by n, etc. 1 minus n minus 1 by n. This will be less than 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by n will be less than 1 by 2 factorial. Therefore, we have 1 plus 1 plus 1 by 2 factorial plus etc. 1 by n factorial. In the previous problem, we have proved this part is less than 3. Therefore, an is less than 3. Therefore, sequence an is bounded above. Then what we have to prove? We have to prove that it is monotonic increasing sequence because it is bounded above. We have to prove that it is monotonic increasing. That is, we have to prove that an is less than or equal to an plus 1, or we have to prove that an plus 1 is greater than or equal to an. Let us take an plus 1. An plus 1 will be from here. It will be 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by n plus 1. So, we are having 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by n plus 1 plus 1 by 3 factorial into 1 minus 1 by n plus 1 into 1 minus 2 by n plus 1 plus etc. plus the last term will be 1 by n plus 1 factorial into 1 minus 1 by n plus 1, 1 minus 2 by n plus 1 plus etc. into etc. 1 minus n by n plus 1. Now, n plus 1 is greater than n. Therefore, 1 by n plus 1 is less than 1 by n. Therefore, minus 1 by n plus 1 is greater than minus n. Therefore, 1 minus 1 by n plus 1 will be greater than 1 minus 1 by n. Therefore, 1 by 2 factorial into 1 minus 1 by n plus 1 is greater than 1 by 2 factorial into 1 minus 1 by n. Therefore, we have the previous statement is greater than 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by n plus etc. Therefore, we have an plus 1 is greater than an. Therefore, sequence an is monotonic increasing. So, we have shown that sequence an is bounded above and sequence an is monotonic increasing. Therefore, by theorem 3.21, sequence an is a convergent sequence. Now we come to the interesting problem, which is connecting problem 1 and problem 2. This problem says we have to show that limit n tends to infinity of 1 plus 1 by n is equal to limit n tends to infinity of 1 plus 1 by 1 factorial plus etc. plus 1 by n factorial is equal to e. That means this sequence and this sequence are same. They converge to the value e. Let us take the nth term of the first sequence an as 1 plus 1 by n, the whole power n. The nth term of the second sequence as bn equal to 1 plus 1 by 1 factorial plus etc. plus 1 by n factorial. From the previous problem, we have an is less than bn for all n. Therefore, limit n tends to infinity of an is less than limit n tends to infinity of bn. Let us mark it as 1. We have proved limit an is less than limit bn. If we prove that limit bn is less than limit an, then we will have limit an is equal to limit bn. Now let us take m is greater than n and we take am. Then am is equal to 1 plus 1 by m the whole power m. This is equal to 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by m plus 1 by 3 factorial into 1 minus 1 by m into 1 minus 2 by m. We will have the nth term, then only mth term because m is greater than m. Therefore, the nth term will be 1 by n factorial into 1 minus 1 by m, etc. 1 minus n minus 1 divided by m plus etc. plus the last term. This will be greater than if we take the terms up to nth term, that is 1 plus etc. plus 1 by n factorial into 1 minus m into etc. 1 minus n minus 1 divided by m. Now we fix n and we allow m tends to infinity. So we are having limit m tends to infinity of am is greater than or equal to 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by m. But m tends to infinity, therefore that becomes 1 minus 0. Therefore we are left out with 1 by 2 factorial plus etc. plus 1 by n factorial, which is bn. Now taking limit n tends to infinity, we have limit m tends to infinity of am is greater than or equal to limit n tends to infinity of bn. We have a mistake here. We have to make it as bn. Yes, we have taken limit as n tends to infinity. Therefore, limit m tends to infinity of am is greater than or equal to limit n tends to infinity of bn. So we are having limit n tends to infinity of an is less than or equal to bn as well as greater than or equal to bn. Therefore, limit n tends to infinity of an is equal to limit n tends to infinity of bn. Already we know that 1 plus 1 by 1 factorial plus etc. plus 1 by n factorial plus etc. equal to e. Therefore, this limit value equal to e. Now let us move on to the fourth problem. The fourth problem says, let an equal to 1 by n plus 1 plus 1 by n plus 2 plus etc. plus 1 by n plus n. We have to show that sequence an converges. First, we are going to prove that it is bounded. Let us take an plus 1 minus an. So, an plus 1 will be 1 by n plus 1 plus 1. Therefore, n plus 2 plus etc. plus n plus 2. That is n plus n 1 plus n plus 1. Therefore, we will have 2n plus 2 minus we have the an. Now, when we subtract, we will be having this n plus 1, 1 by n plus 2 and this 1 by n plus 2 gets cancelled, etc. We are left out with 1 by n plus 1 and 1 by n plus 2 in this expansion. and from this we are having minus 1 by n plus 1. Therefore, keeping 1 by 2n plus 1 as it is and taking LCM, we have 1 by 2n plus 1 plus n plus 1 minus 2n minus 2 divided by 2n plus 2 into n plus 1. Now, taking 1 by 2n plus 1 minus, simplifying this, we are having n plus 1 gets cancelled and we are left out with 1 by 2n plus 2. Taking LCM again, we are having 2n plus 2 minus 2n minus 1 divided by 2n plus 1 into 2n plus 2. Therefore, again 2n gets cancelled. 2 minus 1 is 1. Therefore, we are having 1 divided by 2n plus 1 into 2n plus 2. This is greater than 0. Therefore, we have taken an plus 1 minus an and we proved that it is greater than 0. Therefore, an plus 1 is greater than an. Therefore, sequence an is monotonic increasing sequence. Now, let us take an. An value is 1 by n plus 1 plus 1 by n plus 2 plus etc. plus 1 by n plus n. We are having n plus 1 is greater than n plus 2 is greater than n plus n is greater than n. Therefore, its reciprocal will be less than 1 by n. Therefore, we are having this an is less than 1 by n plus 1 by n plus etc. plus 1 by n. That is n by n, which is equal to 1. Therefore, an is less than 1. Therefore, sequence an is bounded above. Therefore, sequence an is convergent by theorem 3.21. The next problem is an is 1 plus 1 by 2 plus 1 by 3 plus etc. plus 1 by n. We have to show that sequence an diverges to infinity. A1 is 1, A2 is 1 plus 1 by 2, A3 is 1 plus 1 by 2 plus 1 by 3 plus etc. Therefore, sequence an is monotonic increasing sequence. Let us take m is equal to 2 power n minus 1. Then am is equal to 1 plus 1 by 2 plus etc. plus 1 by m. But we have taken m is equal to 2 power n minus 1. Therefore, we are having 1 plus 2 plus etc. plus 1 by 2 power n minus 1. Now, let us group the terms of the sequence. That is, we keep 1 as it is. We combine second and third term. Then we combine 4 terms. Then we combine 8 terms, etc. Therefore, we are having 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus etc. The last pair starts with 2 power n minus 1 and it ends with 2 power n minus 1. Now, let us compare 2 and 3. 2 and 3 are less than 4. Therefore, 1 by 2 and 1 by 3 are greater than 1 by 4. Therefore, we are having the first bracket as 1 by 4 plus 1 by 4, which will be less than 1 by 2 plus 1 by 3. Similarly, 4, 5, 6, 7 are less than 8. Therefore, 1 by 4, 1 by 5, 1 by 6 and 1 by 7 are greater than 1 by 8. Similarly, we are having all the terms in the last bracket will be greater than 1 by 2 power n. Therefore, we are having the first term is 1. The second bracket will become 2 by 4, that is 1 by 2. The third bracket will become 4 by 8, that will be also 1 by 2. The last term will be also 1 by 2. Therefore, except the first term, all other terms are n by 2. Totally n terms, the first term is 1. Therefore, it is n minus 1 power into 1 by 2. Therefore, we are having 1 plus n by 2 minus 1 by 2. Therefore, we are having n by 2 plus 1 by 2. Therefore, taking 1 by 2 outside, 1 by 2 into n plus 1. Therefore, we are having AM is greater than 1 by 2 into n plus 1. Therefore, sequence AN is not bounded above. It is a monotonic increasing sequence and not bounded above. Therefore, it is a divergent sequence. Next, we are going to prove the problem. Sequence n factorial by n power n converges. Let us take the nth term an. An is n factorial divided by n power n. Let us take an by an plus 1. If it is less than 1, we will have an is less than an plus 1. If it is greater than 1, we will have an is greater than an plus 1. Let us find an by an plus 1. That is n factorial by n power n into n plus 1 the whole power n plus 1 divided by n plus 1 factorial. So n plus 1 factorial can be written as n factorial into n plus 1. N plus 1 the whole power n plus 1 can be written as n plus 1 the whole power n into n plus 1. Therefore, n factorial and n factorial gets cancelled. N plus 1 and n plus 1 gets cancelled. We are having n plus 1 divided by 1 the whole power n. The numerator is more than the denominator, the whole power n. Therefore, it is greater than 1. Therefore, an is greater than an plus 1. Therefore, it is a monotonic decreasing sequence. So, we have sequence an is monotonic decreasing sequence. And also, the sequence an is having the numerator value is n factorial, denominator value is n power n. Therefore, the value should be always greater than 0. Therefore, an is greater than 0. Therefore, 0 is the greatest lower bound. Therefore, it is bounded below. Therefore, the sequence is convergent. The next problem is an important problem which is discussing the behavior of the geometric sequence. Let us take the geometric sequence r power n. The r can take the value 0 or the value lying between 0 and 1 or the value equal to 1 or the value greater than 1 or similarly the value may be lying between -1 and 0 or equal to -1 or less than -1. First let us take r is equal to 0. Then sequence r power n reduces to the constant value 0, therefore converges to 0. If we take r is equal to 1, the sequence reduces to the constant sequence 1, 1, 1, therefore it converges to 1. Now let us consider the case r is lying between 0 and 1. In this case, r power n is a monotonic decreasing sequence and also r power n is greater than 0. Therefore, sequence r power n is a monotonic decreasing sequence and bounded below and hence it is convergent. Let us assume that sequence r power n converges to L. Since r power n is greater than 0 for all n, L will be greater than 0. We claim that L is 0. That is, sequence r power n is going to converge to 0. Let epsilon greater than 0 be given. Since r power n converges to L, there exists m belonging to n such that L is less than r power n is less than L plus epsilon for all n greater than or equal to m. Usually we will take L minus epsilon is less than r power n is less than L plus epsilon. But we are here having L value is greater than 0 and L is the limit value. We are taking L is less than r power n less than L plus epsilon for all n greater than or equal to m. We are going to fix n is greater than m. Then we will be having L is less than r power n plus 1. So r power n plus 1 is equal to r into r power n. We are having r power n is less than epsilon. Therefore, this value is less than r into L plus epsilon. Therefore, we are having L is less than r into L plus epsilon using 2 and 3. So, we have L less than r into L plus epsilon. Therefore, L minus RL is less than r epsilon. Therefore, we are having L is less than R divided by 1 minus R into epsilon. Since this is true for every value of epsilon, we are having L is less than or equal to 0 because epsilon is even it can take a very small value. Therefore, R divided by 1 minus R into epsilon is almost equal to 0. We are having L is less than or equal to 0. So we are having L greater than 0 as well as L is less than or equal to 0. Therefore, L equal to 0. Therefore, when 0 less than or less than 1, we are having sequence R power n converges to 0. Now let us take the next case, minus 1 less than or less than 0. Then R power n is equal to minus 1 power n into absolute value of R power n, where 0 less than absolute value of R less than 1. Therefore, by previous case, absolute value of R power n is converging to 0. We know that sequence minus 1 power n is bounded sequence. So we have already saw one important problem 4. That problem 4 says when sequence an converges to 0 and sequence bn is bounded, then sequence an into bn converges to 0. Right? In the same way, we are having that this sequence converges to 0 and this sequence is bounded. Therefore, sequence minus 1 power n into absolute value of R power n converges to 0. Therefore, sequence R power n converges to 0. Now, let us take R is equal to minus 1. Then sequence R power n will become minus 1, 1, minus 1, 1, etc. Therefore, it oscillates finitely. Now, let us take the case when R is greater than 1. When R is greater than 1, 0 is less than 1 by R is less than 1. By case 3, when this value lies between 0 and 1, sequence 1 by R power n converges to 0. We have seen theorem 3.5 which said that if sequence 1 by an converges to 0, then sequence an diverges to infinity. Therefore, sequence R power n diverges to infinity. Now let us take the case R less than minus 1. Then the terms of the sequence R power n are alternatively positive and negative. Also, absolute value of R is greater than 1. Therefore, by previous case, we have absolute value of R power n is unbounded. So we are having sequence R power n is oscillating sequence which is infinite. Therefore, it is an infinitely oscillating sequence. Therefore, if we consolidate all the behaviors, we have sequence R power n converges if minus 1 less than or less than or equal to 1. It diverges if R is greater than 1 and it oscillates if R is less than or equal to minus 1. Thus, we saw the behavior of monotonic sequence. Using that behavior, we have seen some problems which are either monotonically increasing and bounded above or decreasing or bounded below, or it is a divergent sequence. Thank you.